Download this code from codegive.com, link in the description below. Creating amazing textures with code, a comprehensive tutorial. This tutorial will guide you through the process of creating amazing textures using code. We'll cover various techniques, starting with basic noise functions and progressing to more advanced procedural generation methods. We'll use Python with the Pillow library for image manipulation, but the concepts can be adapted to other languages and frameworks. Why procedural textures? Procedural textures are textures generated algorithmically rather than from images. They offer several advantages. Scalability. Procedural textures can be generated at any resolution without loss of quality. Editability. Parameters can be tweaked to create variations of the same texture. Memory efficiency. The texture is defined by a small set of instructions rather than a large image file. Randomness and uniqueness. Procedural generation allows for creating unique and interesting patterns. Prerequisites. Python. Ensure you have Python installed, version 3.6 or later is recommended. Pillow. Install the Pillow library for image manipulation, pip install Pillow. Basic Python knowledge. Familiarity with variables, functions, loops, and basic image concepts. 1. Setting up the environment. Let's start by importing the necessary libraries and defining a basic image creation function. This code creates a basic blank image and saves it to a file. Now, let's add some color. 2. Basic color gradients. A simple way to create a texture is by using gradients. Let's create a vertical gradient. This code generates a vertical grayscale gradient and then a red to blue gradient. Notice how the intensity or red, blue, and green values are calculated based on the y-coordinate and then scaled to the 0 to 255 range for RGB color representation. 3. Random noise. Random noise forms the foundation of many procedural textures. Let's create a simple random noise texture. This code generates a texture where each pixel has a randomly assigned color. This is visually unappealing on its own, but serves as a basis for more complex techniques. 4. Value noise, grayscale. Value noise introduces a level of smoothness compared to pure random noise. Instead of assigning random values to each pixel directly, we assign random values to a grid of points and then interpolate between them. This creates smoother, more natural-looking variations. Explanation of value noise. 1. Grid creation. We create a grid of random numbers, 0.0 to 1.0. The scale parameter controls the density of this grid. A larger scale results in larger blocks of interpolated color. 2. Interpolation. For each pixel in the image, we determine which cell of the grid it falls into. We then use the random values at the four corners of that cell to interpolate the color value for the pixel. Cosine interpolation is used to provide smoother transitions between the random values. Linear interpolation would also work, but results in less visually appealing artifacts. 3. Color assignment. The interpolated value, between 0.0 and 1.0, is then scaled to the 0 to 255 range and used as the grayscale intensity for the pixel. Experiment with the scale parameter to change the level of detail in the noise. 5. Perlin noise, improved value noise. Perlin noise is a more sophisticated noise algorithm that avoids the blocky artifacts sometimes present in value noise. It uses gradient vectors instead of random values at the grid points, resulting in a more organic look. Explanation of Perlin noise. 1. Gradient vectors. Instead of random values, we use gradient vectors at each grid point. Gradient vectors are two-dimensional vectors that point in a particular direction. The dot underscore product underscore grid function calculates the dot product of the gradient vector at each grid point with the vector pointing from that grid point to the pixel being evaluated. 2 dot product asterisk the dot product measures how much the gradient vector is pointing towards the pixel. A higher dot product means the gradient is pointing more directly at the pixel, while a lower, or negative, dot product means it's pointing away. 3 interpolation asterisk the dot products at the 4 corners are interpolated using a smoother interpolation function, often a cubic function, resulting in a smoother, more continuous noise pattern. 4 normalization asterisk the resulting value is normalized to the range 0 to 1, which is then used to calculate the intensity of the pixel. Key improvements over value noise asterisk. Asterisk gradients asterisk using gradient vectors gives the noise a more natural, flowing look. Asterisk smoother interpolation asterisk the interpolation function is designed to minimize artifacts and create smoother transitions. 6. Fractal Brownian motion, FBM, / multiple octaves. FBM is a technique that combines multiple layers, octaves, of noise at different scales to create more detailed and interesting textures. Each octave adds finer details to the underlying noise. Explanation of FBM asterisk. 1 octaves asterisk the octaves parameter determines how many layers of noise are combined. More octaves mean more detail. 2 lacunarity asterisk the lacunarity parameter controls how the frequency of each octave changes. A higher lacunarity means each subsequent octave has a higher frequency, smaller features. A lacunarity of 2.0 is common, meaning each octave has twice the frequency of the previous one. 3 persistence asterisk the persistence parameter controls how the amplitude of each octave changes. A lower persistence means each subsequent octave has a lower amplitude, less influence. A persistence of 0.5 is common, meaning each octave has half the amplitude of the previous one. 4 scale asterisk the scale parameter determines the initial scale of the first octave. 5 combination asterisk the code iterates through each octave, sampling the noise function at a different frequency and amplitude, and adding the results together. Experiment with the octaves, lacunarity, persistence, and scale parameters to create different types of textures. 7. Adding color and applying palettes. So far, we've mostly generated grayscale textures. Let's add some color. This code takes a grayscale FBM image and colorizes it by interpolating between 2 specified colors based on the grayscale value of each pixel. 8. Creating more complex patterns, Voronoi and cellular automata, beyond the scope of basic noise. While noise functions are fundamental, we can also create textures using entirely different algorithmic approaches. 2 popular techniques are Voronoi diagrams and cellular automata. Voronoi diagrams asterisk. A Voronoi diagram divides a plane into regions based on the closest point in a given set of points. This can be used to create cell-like patterns. Explanation asterisk. 1 cell generation asterisk random points, cell centers, are created. 2 distance calculation asterisk for each pixel, the distance to each cell center is calculated. 3 cell assignment asterisk the pixel is assigned to the closest cell center. 4 coloring asterisk the pixel is colored based on the index of the assigned cell, or any other rule you define. Cellular automata asterisk. Cellular automata are discrete models that consist of a grid of cells, each of which can be in one of a finite number of states. The state of each cell is updated based on the states of its neighboring cells, according to a fixed set of rules. They are great for creating organic and emergent patterns. Explanation asterisk. 1 Initial state *. The automaton starts with an initial state, typically a single alive cell in the middle. 2 Rule set *. A rule set defines how each cell's state is updated based on the states of its neighbors. Elementary cellular automata, like the one above, consider the states of the left, center, and right neighbors. There are 256 possible rules, numbered 0 to 255, Wolfram rule numbers. 3 Update * For each generation, the code iterates through each cell and applies the rule to determine its new state. 4 Image representation *. The state of each cell is then mapped to a color, example black for dead, white for alive, and drawn in the image. Limitations and further exploration *. Performance * Complex procedural textures can be computationally intensive. Optimization techniques, like caching intermediate results, may be needed for real-time applications. Parameter tuning * Finding the right parameters to create the desired texture can be challenging. More complex cellular automata * The example provided is a very simple 1D cellular automaton. More complex 2D and 3D cellular automata with different neighborhood definitions and rule sets can create incredibly rich patterns. GPU acceleration * For real-time or high-resolution texture generation, consider using GPU acceleration, example with OpenGL or CUDA. Shader programming * Shaders, GLSL, HLSL, are specialized languages designed for image processing on the GPU. They offer excellent performance for procedural texture generation. Combining techniques * The real power of procedural texturing comes from combining different techniques. For example, you could use FBM to modulate the color of a Voronoi diagram, or use cellular automata to define the shape of objects in a scene. Conclusion. This tutorial provided a starting point for exploring the fascinating world of procedural textures. By understanding the fundamental concepts of noise, interpolation, and algorithmic pattern generation, you can create an endless variety of unique and visually stunning textures. Remember to experiment with different parameters, combine techniques, and explore advanced concepts to unlock the full potential of procedural texturing. Good luck!